There we go. All right, so I will start with a reminder that quite a few people have not have they still have a blank for the prerequisite quote unquote assignment, which means I was not able to clear the prerequisite requirement for those particular people, and they have not submitted a copy of their prerequisite challenge petition. So that means, I do not see anything in progress to meet the requirement. The assignment has a due date. By the time we get to the due date, and I still do not see any evidence of a petition in progress, I will drop those people. So if you want to make sure that you're still in class, you want to check your grade for that protocol assignment. If you get a one, it's good. Okay, that means somehow I was able to check your prerequisite requirement and you're cleared already. So if you got a one, you don't have anything to worry about. If you get a zero or a dash, basically it means there's no grade. Then you should you should do something. Okay, that there are actions that you should probably uh, take in order to make sure that you stay in class because of the prerequisite requirements. So, do we have any questions about the prerequisite requirement for this class? Yep. Say again. You send your Yeah, but you have to upload a copy to the assignment too, because I. Sorry. Okay, but that does not meet the what the assignment is saying. So you have to upload a copy of that to over here because I do not know whether they approve or not, and I have no idea how long it takes for those guys to get the whole thing through the route because it has to go through the instructor and then the dean and then go to enrollment services and then back to me. So just upload a copy so I know it is in progress. That's all I need to know. Yep. All right. So that's one. The second one is RAD. Okay, and from not just this class, but from my other CISP 310 class as well as CISP 440, I think the RAD program can offer. It can be useful to certain people in the class. Does everybody know what is RAD as an acronym? Okay, RAD stands for Reading Across Disciplines. It is a program on this campus where people can enroll in I think point 0.5 or 1 unit of your classes where they will teach people how to. Okay, I know it's gonna sound stupid. How to read? Okay, and people go like, yeah, I know how to read. by the end of most of the by the end of the semester, in many of my classes, people would complain. It's like, oh, you write in a way that I cannot understand. Well, but that's not what the other part of the class has to say. So it takes a kind of skill to read technical stuff. Okay, and basically all the teaching material for this class are technical. So RED is a program that can help people understand, okay, in order to read technical stuff like textbooks, especially in the STEM subject area, this is what you can do to help you, read and understand the material in a more efficient way. So I will try to get the RAD people to come here to kind of do a 5 minute or 10 minute spiel. Um, I think their sessions start about 2 weeks into the semester, so we still have time to sign up for those classes, and it might be useful for certain people in this class. All right. So with both of those talked about, and we can now get started. So last time we talked about the circuitry that used two p transistors and two n transistors. So I'm going to redraw the picture. I can do it in Logisim, but I can also just hand draw that whole thing. So we basically have power, okay, and then we have two p type transistors, and which way they orient is not super important. So these are the two p type transistors. We also have two n type transistors. There we go. And then we have ground. And for the N-type transistors, the direction goes in this way. I finished grading the submission from the lab on Tuesday. Most people got perfect score, okay, but a few people, get less than perfect score. One person turned in the file using the wrong file name, so I typically do not take points off. But because the file name has a space in it, and I have to do special things to get it to run again, so for that one, I take 1 point off. And then some people turn in a circuit that is not really a circuit. So, for those kind of submission, it's a zero. And then some people turn in a circuit that does not, it's close to what the circuit is supposed to be, but definitely shows evidence that the instructions were not followed. So, those also get points off. So basically, if it works perfectly, it's going to be a 4 out of 4. If it is like missing a few cases, it might be a 3 out of 4 or 2 out of 4. If the circuit is not even there, like I don't even see transistors, it's a 0 out of 4. And if the circuit is like, it resembles what I do in class, but it does not resemble what the instruction of the lab is telling people to do, then it is a 1 out of 4. So that's kind of the grading scheme. So just want to bring that up. And we'll go ahead and finish this circuit here. Like that. And over here, this connects here, this connects here. And then we have both of these connected together, and it goes to one of the input pins. And then these two connect to, and it goes to another input pin. And this is where we take the output pin. All right. So do we have any questions about the circuit itself? Okay. And the biggest, the bigger question is, what does it do? So I think I mentioned, this is a negated AND gate on Tuesday. Is that correct? Okay. So the question is, but it's not one of the gates that we know. Okay. In other words, if I say, this is X NAND, which is negated AND Y, it really is the same thing as in C and C++ notation. It is X and Y, except it is negated. So X NAND Y is exactly the same thing as the negation of X logical AND Y. So it's not one of those operators that you're used to. It was never introduced in CISP 360, and I really doubt that it will be introduced in any of your CIS classes here. But the thing is, if I have this, I can then use this to make logical gates to do all the usual logical operations. So the mathematical symbol for X NAND Y is this symbol here. It's an up arrow. Okay, so all of this stuff is in the module, the reading material. So if you have read the reading material ahead of time, this is all like boring stuff, okay? Because there's nothing new of what I'm talking about here. So this is one thing that I'm gonna nag, okay? Since I'm a father, I do tend to nag a little bit. I know you are not my kids, but it's a habit. Okay, when I see young people, and I go like, okay, go into nag mode, which I know is not effective, but nonetheless, I still want to do it. Okay, so for people who look at this and go like, oh yeah, I totally get this because I have read the entire module already, and you even talked about this on Tuesday. I got it in my notes. Great. Okay, so you are doing everything that you can to stay on top of things. Okay, for people who go like, well, I vaguely remember because I remember what you talked about in class on Tuesday. um, that's good too because you're paying attention on Tuesday, but it means that you might need to review the material from a previous class. Okay, and then for people who look at this and go like, I have no idea what this is, I have no idea what is NAND nor the circuit, then I would start to worry. Okay, so that's just me, telling you, just from experience, teaching this class, the trajectory based on just the first lab. Okay, how the whole semester is going to go. All right, so this is X NAND Y. So how do we do a negation using just NAND? That's the first question. Okay, it's just X NAND X. So just by using a NAND gate, I can now say, oh, I can do just regular negation now. Is that okay? Do we kind of understand what I'm talking about here? Not so much a proof of why this works or how this works. Just the fact that hey, we can implement negation just using NAND. In other words, if I spell this out entirely, this simply means the negation of x is the same thing as the negation of x logical and, whoops, back. There we go. There we go. Okay, that's ugly. There we go. So can we buy this? Can we buy the negation of x is the negation of x and x? Yes. Does everybody buy that x and x is really just x? Why do you have that extra conjunction when you don't have to have it? Okay. So this one is easy. Okay, negation. We can do negation. So what about x and y without the negation? Well, let's look at this trick here. This is the negation of x and y. Even without introducing Boolean algebra, I hope most people can see that double negation cancels out. Are we good so far? All right. So the inner negation, we are looking at, okay, where's my cursor? There we go. So we are looking at this negation and this and here. Hey, it is the negation of an and. That is NAND. Is that okay? So we can now rewrite this as the negation of just x NAND y. Because it's just switching from the long way of saying the negation of an and to the operator that means exactly the same thing. Are we good so far? So now we are boiling down to, oh, but we have to negate that in here. Do we know how to negate something now? Just look up one line. Yes, we do, right? So instead of having just x NAND x, we're going to take this whole thing here and use a NAND itself. So now this becomes x NAND y, the whole thing, NAND itself. And now we have just regular conjunction, regular logical AND. All right? Is that okay? So this is not really linear, Boolean algebra. This is really just kind of, it's based on pretty intuitive stuff, okay? The next one does involve your Boolean algebra because it has to do with OR, and then we have to use deMorgan's law. deMorgan's law will be introduced later on when we talk about binary addition, but this is like an earlier introduction to deMorgan's law. So now we want to look at x or y, and we say, how do we translate this into just using NAND operator? Okay, because I just want to emphasize why the NAND operator is like the universal binary operator, because we can use that to emulate any one of the other logical operator that we are familiar with. Okay, so let's take a look at this. And I'm going to use the same trick here and say, if I double negate it, it means I did not do anything useful. Is that okay? Because negation negates negation, so double negation cancels out, and then we just ended up not really doing anything useful. Okay, so here is the part about deMorgan's law. So deMorgan's law goes like this. Okay, so deMorgan's law said if you negate x or y, then it really is the same thing as not x the whole thing and not y the whole thing. That's deMorgan's law. So I just told you a statement and I claim it to be true. What are you going to do? You just kind of write it down and say, the test says so, it has to be true. Well, no. You want to kind of go like, okay, this looks suspicious, okay? It looks dubious. How do I know whether this is true or not? Whether your text claim that the left-hand side equals to the right-hand side is true or not? So what do? There are a few ways you can proceed. You can go onto the internet, look up deMorgan's law. right? You can double check and at least find that, oh, okay, Wikipedia says so, and then you can also go to Mathematica and some of the other websites. They are more you know those are the websites where you can count on. Okay, and but there's one more way to do it. You can check it yourself. You can basically say X can be true or false, Y can be true or false. I'm going to use a truth table to double check this. How many people are familiar with the concept of a truth table? Okay, a few. Okay, so I'm going to introduce the idea because it is going to be useful not only in this class, but also in many of your other classes, especially if you are in computer science. So a truth table has independent variables. So in this case, we have two independent variables. The phrase independent variables is just as it seems. Okay, the variables do not depend on each other. The value of x does not depend on the value of y. The value of y does not depend on the value of x. So if x and y are Boolean, what can be their values? Yeah, true or false. Very good. Okay, so x can be false and x can be true. While x is false, y can be false or true. While x is true, x can also be false or true. Does that make sense? So I have just enumerated all the possible ways to combine the values of x versus the value of y. There are only four ways to do this. Is that okay? So now I have to look at the expression, the expression that I have listed here and say, okay, so if x is false, y is false, what is not x the whole thing? Logical and not y the whole thing. Well, not x is going to be true, not y is also going to be true. Then we end up with true and true. So this expression using this column is going to be true here. What about the next row? What do you think? X is false, so not x is true. Y is true, not y is false. So we end up with true and false, which is false. Okay? This one is kind of symmetric. The third row is kind of symmetric to the second row, so it's going to be false as well. And then the last row, we have both x being and y being true, which means the negation of both of those are going to be false. So we end up with false and false, which means it is also false over here. So that's for this label. And then for this particular expression, you do exactly the same thing. Okay, you evaluate the expression for every single row based on the value of x and the value of y. And I will just tell you that if you actually go ahead and do it, you will end up with exactly the same values. It will be true, false, false, false. So that established that the two expressions are indeed equivalent because for every single way you can have a value for x and a value of y, the expressions, the two of those expressions, they come up with exactly the same value. So we have just proven that the two expressions are the same without using algebra whatsoever because we spelled out every single possible case, and for every single possible case, the two expressions gave me exactly the same answer. Is that okay? All right. It's a very useful tool. Okay, it is a very useful tool. I would encourage you guys to kind of get used to it, because it's going to be helpful down the line. All right. So this is deMorgan's law, and I look at deMorgan's law, and I go like, oh, I can apply deMorgan's law because look at this sub expression here. Look at this sub expression here. It looks exactly the same as this expression over here, which means I can replace it by this expression here. Now that is usual, just regular algebra approach, right? You recognize a pattern, you apply the pattern, and then you transform an expression into a different form, but it gives you the same value. Okay, so we'll do it that way. So we have not x and not y, like so. Okay. You look at this and go like, huh, I think I recognize the negation of an and. Do you? I see the negation of this and over here. The negation of an and Oh, that's a NAND. So that means I can now replace the negation of an AND with the NAND operator. It's really just a shorthand. Okay, so there we go. So we have now not X, the entire thing, NAND, not Y, the entire thing. You go like, but wait, we're not done yet. Because we don't have negation, we are only supposed to use NAND. So now I have to look at the negation of X and go like, how do we use a NAND operator here? We talked about it, right? We just talked about it in the previous slide. If I have the negation of X, it is the same thing as X NAND X. So I can just use this trick here and change this expression to X NAND X NAND Y NAND Y. So I have just transformed a regular logical OR into something that makes use of just NAND. Is it messier than before? Yes. Is it going to be faster to compute? No. So what is the whole point of this? I can use P and N transistors to implement the usual regular logical OR. That is the bottom line. Are we doing this? Are we doing okay with that concept?
So the NAND's like an arrow?
Yeah, so that's the symbol for of NAND. And getting back to the notes here. So if we are to go back to physical states, because this is where we left off, I think we just finished the entire module or close to finishing the entire module. So at the very end of this module, there's the NAND operator is sometimes denoted as the up arrow. So that's why reading the notes is useful. I know it is boring. I'm not the best person to write a textbook. I tend to be terse. Quite terse, sometimes. But all the information is in the module. So reading the module ahead of time can really help prepare you for the class because your mind is already going like, okay, I got all this and this and that. And then by the time we talk about it in class, it's a reinforcement. So the lecture should be a more or less a reinforcement and also a Q&A session when it comes to the content of the material. It should not be the only source or the first contact with the content of this class. And you will probably find a four-year university would use exactly the same approach, except a little bit more extreme than I am. Well, okay, that depends on which four-year university. If you're going to Berkeley, you don't even get to see the professor. I'm not kidding you. Um, so, so I'm just trying to help you guys prepare for your journey once you get past here. All right, so numbers and values. So this is a transition to the next module. So now we have transistors, okay? We talked about transistors. We talked about the NAND gate. We talked about how the NAND gate can be used to make logical AND, logical OR, logical NOT, okay? And all of these are Boolean, okay? In other words, the only two values we can deal with all of these mechanisms is true or false. So we can look at true as 1 and then false as 0. Great, we have two digits that we can deal with now, 0 and 1. But that's all you need for binary numbers. But then you look at the way you do numbers, it's like, but we don't do binary numbers on the daily life in daily life. I think we should, but there are reasons why we do not. So now we have to talk about base conversion. How do you convert a value so that it can be represented in different bases? And by default, we use base 10. Not always, okay? Not always, because when you look at how pounds and ounces work, that is not base 10, because there are how many ounces in a pound? 16, very good. And there are 60 seconds to a minute, 60 seconds to a minute, 60 minutes to an hour, and then 24 hours to a day. So we actually regularly deal with things that are not base 10, even though we do represent the minute in an hour in base 10, but to roll over to the next hour, that's not base 10 at all. Okay, so we are transitioning from this slide to the next topic. And the next topic, if we just go for the links, like this, we have the video to show how to use CLI in Windows and Linux and Mac OS 10. Um, that's really important because we are going to use the command line stuff a lot in this class. I hope you guys had a chance to watch that video. This one useful, but not as useful. But it's useful in the sense that you can test your own circuit before you turn it in. So that way, if your circuit works 100% when you're testing it, you're going to get a 4 out of 4. No need to worry about anything like maybe it doesn't work when tech is testing it. Nope, this is exactly how I am going to test it. So what we're going to do is we are moving on to values, numbers, and bases. So this is our next slide, and this is a great time to take row as well. So you can see that I have the row already prepared today. You cannot see it yet because I have not shown it, so it's hidden right now to you. But I do want to kind of get in first so I can show you the passcode because you will need that passcode to get into the activity. So you want to sign in first, okay? If you have not signed into Canvas already, do so now. And then I'll show you the passcode to get into this activity to tell me that, yes, I am in class today. All right, so the way it is done is we go to settings and then show access code, and it is base. But not BASE, it is BASS. I intentionally used the other base because I care about this base just as much I care about the other base. Oh, I have not unhidden the activity. Give me a second. Let me go all the way back. Okay. So when I say refresh, then you should be able to see it. So give me a second here. All right, so go ahead and refresh your browser. You should be able to see the row taking activity right below values, numbers, and bases. And I believe you have until 9:40 a.m. to do this. I hope that is sufficient time. Yep.
It says no preview available on the roll.
Huh. No preview available. So you cannot participate?
Yeah.
Hmm.
It just says add a comment to the side and save.
You have to click the link at the top. It says assignments, and then it says comment. Next to it, click on that. Go back. The link on the right of your side. 2020 roll meeting.
Here.
Yeah. Next, on the right, on the right.
Oh,
Okay. So back. So can the rest of the class get through this? Okay, it was okay? All right. Well, let me switch to student view and see if I can do it. All right, so we go to rotating. Yeah, I can do it. It's right over here. So it's BASS as the access code. Submit. Okay, begin. And it has one single question that is really hard to answer incorrectly, but I guess some people can intentionally try to answer it incorrectly. There we go. So I am present. Cool. All right. So I'm hoping everybody got this one. Okay, no one has any problems. Okay. Alrighty. So we are going to talk about values, numbers, and bases. All right. So this is a pretty long module. It's a lot of reading. Once again, okay, your RAD can help you give you some techniques and skills, to get through, reading, digging through stuff like this. So the lecture, once again, is a reinforcement. Okay, I give you live examples so that we can actually go do some of the base conversion stuff in class. So it's more dynamic than just reading the text. But once again, the lecture is not a replacement, okay? It is not a substitute for reading the material that are already linked from Canvas. So do not, just rely on the lecture. Just because some people can do that does not mean, on the average, everybody should be able to do it. I said that because, I am one of those people. I just bring myself to a lecture and I can absorb most of the information from the lecture itself. Okay, so we're going to switch back to, let me see, there you go. So we're going to switch back to the tablet, and this time we'll talk about how to make change for a certain amount. And we are in the United States, so we're going to use US currency and the denomination thereof in order to make change. So in this class, I'm going to pick a different number from the other class. I'm going to pick $25 and 25 cents. Okay, that looks good. Okay, so you're working at McDonald's, okay, and as a clerk, over there, you need to make change for a customer for $25.25. Now, why would that be the change amount when you're working for McDonald's? I have no idea, but that is what you need to do. So the question is, instead of giving the customer 2,525 pennies, which is one way to do it, probably not a good way to do it, but that's one way to do it. But can you figure out how to use the least number of bills and the least number of coins to come up with exactly the same amount? That's the question. So, how many of you think that you kind of have what it takes to work at McDonald's, to do exactly this? Okay, I think I qualify. Okay, so let's go ahead and do it anyway. Okay, so from your perspective, you go like, okay, we need one $20 bill, we need one $5 bill, and then we just need a quarter. That's it. Three things, and it will make the exact change. Is that right? Okay. So how many of you did this? Okay, figuring out the number of bills and coins using an app, a piece of paper? No, you all did it in your mind, which means you already know how to you already know how to convert between bases. You just don't know it yet. Okay. How many have kung fu movies use that line? You already have the skill. You already know how to do this. You just do not know that you already know. All right? So I'm going to translate what you knew about making change into base conversion. Is that okay? But before we do that, it is important to spell out why that skill is transferable from something that you know and you are very familiar with to something that you think is actually much harder. Okay, so we'll go ahead and look at the U.S. Currency denomination. So we'll start with a $50. Okay, so that's the $50 bill is probably the highest bill in the cashier at a McDonald's. So what is the next one down? 20, right? And what is the next one down? 10, and the next one down? 5, and next one down. I'm not counting the unusual one, just the usual ones. 1, okay? And then we are moving into coins now, not counting the unusual ones. What is the common coin that is right below a dollar? A quarter, okay? And then a dime, and then nickel, and then a penny. Oh, okay, forgot zeros. So this is a '05, this is a '01. There we go. All right, let's look at the multiplier. to go from one, to the next one. So we'll start with a penny. To get from a penny to a nickel, it's a multiply by 5. To get from a nickel to a dime, it's a multiplication by 2. This is not even an integer, it is 2.5. And then the next one is not even a number that we have seen so far because it is a 4. And then we go back to a 2. And you would think, oh, no, it's a 5. So this is a 4, this is a 5. And then you would think, oh, so we are restarting from the beginning because the 1 is kind of corresponding to the 0.01. So the next one is going to be um, 5. And then we have the 2 again. You are correct that we have a 2 here. And then you're expecting maybe it's another 2.5, then the pattern repeats, right? No, we have a 2 here. And then we have the 2.5. So do we see any repeating patterns at all? No, there's no repeating pattern. And yet, you can do all of this stuff here in your head without even a piece of paper. Why do you think that is the case? You have done it enough times, okay, that there is enough pathway in your brain that you can do this. It's just your muscle memory, okay, or the equivalence of muscle memory in your head for doing this sort of arithmetics, okay. But what is the method? Okay, if it boils down to the method, what was the logic that you figure out that you need a $20 bill and you skip the $10 bill, go straight to the $5 bill to make up for $25.25? In your head, you were doing comparison. Okay, do I need a $50 bill? No, because $25 something is less than $50, so we don't need a $50 bill. What about $20 bill? Yeah, we need at least one $20 bill because 25 something is greater than or equal to 20. That's a logical decision. How many do we need? 25 divided by 20 is 1 point blah blah blah. Okay, so we need one $20 bill. Then you take that $20 of the $20 bill off of the $25.25 because you already have that accounted for. So you have $5.25 left. So then you apply the same logic again. Moving down to the $10 denomination, it's like, do we need a $10 bill? No, because 5 is less than 10. And then you move down to the $5 bill. You go like, how many of the $5 bills do we need? Well, let's divide. 5.25 divided by 5 is 1 point blah, blah, blah. So we need one $5 bill, and so on. So there's a logic that you did in your head, even though it was probably mostly subconscious. Because most people cannot just, did what I just said. Okay, these are the steps that I was taking subconsciously to figure out the answer. But that is exactly what is going on in your head, even though you were not aware of it. I'm just bringing that to the foreground so that now you are aware of how you did the math just subconsciously. Are we doing okay so far with this example? Okay, excellent. So what I would propose is we change the currency system, we change the denomination as such. So we still have a dollar, $1 bill here. Okay. The next one is a $2 bill. The next one is $4 bill. The next one is. Can anyone guess what's the next one's gonna be? 8. Very good. And then the next one up, 16. And we'll just move one more. Okay, 32. And what about this way? The opposite way. If this is the pattern, what do you think is the largest, uh, the coin that has the most value? Hmm? Sorry? 50. Okay, half a dollar. Very good. So we have a half dollar here. And then what about the next one down? 0.25, a quarter of a dollar. And then the next one, if I want to have one more, 125, which is an eighth. Okay, oops. I almost wrote 128. This is 125. Okay. So from the perspective of a foreigner, okay, somebody who just immigrated into the United States, which currency system do you think is more friendly? The one to the left or the one to the right? one to the right. Okay, because you don't have to memorize. It's like, oh, the next one up is this much more, but there's no pattern to it, so you have to memorize. The one to the right is like, okay, there's one thing to remember: two. Everything is two times or two or divided by two from the next one. Okay, so all right, but it's awkward, right? So now I'm asking you to make change for exactly the same amount, okay, which is $25.25. But this time we are going to use the strange, currency system, the strange denomination system. So how would you do it? Okay, first of all, I know how you're feeling. You're feeling, oh, this is awkward. This doesn't feel right. Okay, but that's okay because we are used to base 10. Why are we used to base 10? Why do we use base 10 by default? I will list a few reasons. Okay, initially, okay, maybe thousands, maybe even longer ago, it had to do with we got 10 fingers, 10 digits. Okay, and then that became a convention, a tradition, and stuff like that. And then most people are doing it that way. So if you go, okay, I'm gonna roll all the way back to elementary school. So if an elementary schooler go to the teacher and go like, base 10 sucks because the multiplication table is huge and I don't want to memorize all that stuff. I heard base 2 is so much easier because there are only 4 entries I have to remember in the multiplication table. The teacher will say, yeah, but we don't teach base 2 here. Why? Why are you asking why all the time? Just deal with base 10. So, in other words, the kindergarten elementary school teacher is not even examining, the merit of switching from base 10 to base 2. We just keep the momentum going. We don't question why it is like that. It's just that this is the way we have been doing it, and we are going to do it this way because I don't want to cause trouble. Because if the elementary school teacher says, you know, that makes sense. It makes my job a whole lot easier too. Instead of spending 2 months to make sure that you guys remember the multiplication table, this is done in a week. We can go have fun. We can have field trips for the next 3 weeks. Woohoo! Yes. But the elementary school teacher cannot do that, right? Because then you have to run up to the principal, the school board, the textbook, and the publishers, and so on and so forth. So that's how we keep that momentum going, even though it does not make sense. When was the last time you actually counted fingers to figure out, some kind of arithmetics? It doesn't make sense to use base 10 anymore. We don't use our fingers for counting anymore. Okay? Well, enough rant. That's why I cannot be a politician. Because, changes that need to be made make sense to me, but most people go like, ugh, that doesn't feel comfortable. But it makes sense. This is the logical way of doing it. Ugh, I don't like logic. Okay, so getting back to this one. So how do we figure out how many bills and coins we need after we switch to the new currency system in order to make up for $25.25? It's the same approach. Okay, you start with the 32, you go like, 32 is more than 25, none of those. Okay, none of those. Then you move down to 16, you go like, 25.25 is greater than or equal to 16. We're going to have one of these. You don't even have to do division. It is literally just compare. If it is greater than or equal to, you have one, and if not, you have zero. There's no division involved. And then you move down one more, you go like 8. So after we take care of the 16, we have how much left? Remember, we got $25 to begin with, so we got $9 left, right? So when you move down to the 8, we go like, 9.25 is greater than or equal to 8. Let's pick up one of those things. Then you have $1.25 left. But you move down to the $4 bills, you go like, we don't need a $4 bill. We don't need a $2 bill. We need $1 bill. Then you have a quarter of a dollar left. You go down to the half dollar. You go like, nah, we don't need one of those. We need one of these, and we need none of those. Okay, so in the end, you end up with $1 $16, $1 $8, one half. Oh, I take it back. We do not need a half dollar. We need. Oh, okay. I was just misreading my own thing. 116, 18, 11. Okay, I was misaligning the reading, and then one quarter of a dollar. That's base conversion. We have just done base conversion from base 10 to base 2. Was that hard? Was it painful? It feels a little strange, right? But it's not that bad. Okay? So I don't see a binary number. I see a bunch of zeros and ones, but I don't see a number. Well, let's make a number out of this. If I were to make a number out of this, I would put a decimal point here, or binary point, because it's not decimal anymore. And I'll tilt my head like that, clockwise 90 degrees. To save you a trip to the chiropractor, I'm going to rewrite the number so you don't have to tilt your head. So this becomes the most significant digit, or the most significant bit in this case. This becomes the least significant bit. So the way we write this is 0.010. And I put a 2 here as a subscript to emphasize that this is a base 2 number. So this base 2 number is representing exactly the same quantity as 25.25, and I'll emphasize this is a base 10 number. We have just gone through a base conversion. Any questions? Okay, let me ask you this. Are you convinced that you know how to convert from a base 10 number to a base 2 number? Can you replicate the steps? If I give you a different value, can you replicate these steps to give me the binary representation of a number that is in base 10? Okay, I see a few nods. Okay, I don't see a whole lot of frowning or turning of the head. This is why I like to teach in person, because it's easier to read that. Because if I were to teach this class on Discord or on Zoom, I just see a whole bunch of static pictures of people's avatar. They go like, okay, are there any questions? And there's absolutely no feedback. I know none of you actually gave me an audible feedback, but just from glancing around the room, I can kind of tell that, okay, you guys are getting it. Okay, good. But with online teaching, there's zero. There's no clue whatsoever that I can use. That's okay. No problem. All right. So what about the other way around? If I give you a binary number, can we figure out the base 10 representation? Well, let's give that a try. All right. So I'll give you a number, 101.101. Okay, there we go. This is a base 2 number. I want to convert this to base 10. How would you do that? Now, if this is the first time that you do base conversion from base 2 back to base 10, one tool that will really help is really just to list all the powers of 2. Okay? So I'm going to start with a little row here, not even the table. I will say 1 is 2 to the power of 0. 2 is 2 to the power of 1. 4 is 2 to the power of 2. 8 is 2 to the power of 3. That's sufficient for this example, but I'm going to extend it one more just to let me know where it's going to go. And then on the opposite side, we have 1 half, or 0.5, being 2 to the power of negative 1. 0.25 is 2 to the power of negative 2. And then 0.125 is 2 to the power of negative 3, and so on. So I'm going to have a little list here to help myself. Okay? Are we good so far? All right. Is everybody in this class comfortable with an exponent that is negative? 2 to the power of negative 3 is 1 divided by 2 to the power of 3, which is 1/8. So is everybody comfortable with exponents? Because if not, I'm not kidding now. If not, it really, those people should go back and take college algebra first, because exponents play a very important part in computer science. So instead of trying to kind of push through a class and not really fully understanding the mathematics, it's much better to have a foundation than go ahead and complete the computer science class. All right, so having said that, the rest is really just addition. But how do I know how many of each power of 2 do I have? So the trick is this is an indicator. This separates the 2 to the power of 0 from the 2 to the power of -1. So the point, okay, is actually a anchor so that we know how to read the digits of a number. So on this side, we have 2 to the power of 0. On the other side, we have 2 to the power of -1. So this digit corresponds to 2 to the power of 0. This corresponds to 2 to the power of 1. This corresponds to 2 to the power of 2. And this corresponds to 2 to the power of 3. This corresponds, oh, okay, I take that back. So this one corresponds to the number of 2 to the power of -1. This tells me how many 2 to the power of 2, -2 do I have. And this one tells me how many 2 to the power of -3 that I have. Oh, okay. Nobody told me that this is how a number works. Well, do you think this is how a number works only in base 2? Or do you think this is actually how it works for base 10 numbers as well? This is also how it works for base 10 number, except in the base 10 number, instead of asking about 2 to the power of something, it is 10 to the power of something. But the structure of a number is still the same. Each digit is really just telling us the quantity of a specific power of the base. If you're dealing with base 10, it's 10 to the power of something. When you're dealing with binary, it is 2 to the power of something. But the structure does not change. It really is the same. Okay, so all I'm doing is changing 10 to 2 when I'm dealing with base 2. All right, so getting back to this example, can we figure out the answer? Well, yes, because we have an 8 here, okay? We have a 4, we have a 1, and then we have a half, okay? And then we have an eighth. So add these up, and then we have the final answer. So we have 8 plus 4 plus 1, which is a 13, and then we have the 0.5 and the 1.125. So the answer is 13.625 in base 10. That is the same thing as 1101.101 in base 2. Are we doing okay so far? Because I have just done the conversion in two ways. You are given a base 10 number, which you're familiar with, and we can convert it into base 2. And then this one is we are given a base 2 number, and we're converting it back into a base 10 representation. So one thing I forgot to say is the difference between a number versus a value. How are those things different? Well, what do you think? I want you guys to think about it first, and then I'll give you what I think of it. So, what is the difference between a value versus a number? Yes.
Certain values, like true and false, are assigned to numbers like 0 and 1.
Okay, that is a good point too, but not quite what I'm thinking of. Okay, so if I hold up my hand, and this is my hand, okay, what you see is a value. What you see is a quantity. The number of fingers sticking up is a value. It is not a number. Okay. Now, when you try to tell the person next to you and say, "Oh, Tech is holding up 8 fingers," 8 is a number. It is a representation of the quantity. What do you mean by representation? I have no idea what is representation versus what is a number, and how does that have anything to do with the value? It's easy. Okay, I can speak Cantonese. So to you, this is 8. When you write it down, and you type it on the keyboard, you look at the key that has the digit 8 in it, and you press that key. That's 8. Okay, but in Cantonese, bat. Okay, there are bat fingers. Okay, that I'm holding up. So you go like, but this is not a Cantonese class. Did I walk into the wrong class? No, this is a computer science class. But the point is, baht is the Cantonese representation of this quantity. So when you're talking with someone who understands Cantonese, that representation is going to it will get the value across. Okay, the other person will understand. But in a class like this, when I say 8, everybody know the English word what 8 is representing. It is the quantity of this. So the representation is only a way to store information and a way to exchange information. When you need to talk to someone else, when you need to convey how much, how many, then you need to find out, okay, what is the common understanding here? Is that okay? So what does that have anything to do with what we have just done? Both of these are two representations of the same value. Okay, a number is nothing more than a representation of a value, but a value can have almost an infinite number of representations because we can change the base. Are we doing okay so far with all the concepts? So I'm not only introducing methods of doing things, but also introducing concepts, value versus numbers, base 2 versus base 10, and stuff like that. All right. Okay. So this is all good. Okay, having examples is helpful, to illustrate concepts. But when we get back into the notes, there are stuff that is kind of like, what is that? Okay, so I'm gonna skip all the way to. I mean, this is all, Okay, we can talk about this a little bit here. Where the mouse pointer is. 16.375 is a base 10 number. What is it? It is 10 plus 6 plus zero point 0.3 plus zero point 0.07 plus 0.005. Okay, what is special about that? Well, I can rewrite the 10 as 1 times 10 to the power of 1. I can rewrite the 6 as 6 times 10 to the power of 0. I can rewrite the zero point 0.3 to 3 times 10 to the power of negative 1, and so on. You go like, okay, Tack, you're just making things unnecessarily more complex, right? Because we started off with a nice, easy representation, okay? And I have to turn it into first an expression of addition, and then I turn it into a summation of products involving powers. It's like, why? Why make it more complicated? What kind of pattern are you seeing? As the last form, where it is a sum of quantities of powers of 10. Yes,
Kind of looks like a ring and sum or a limit.
it is it's a general pattern. It's a much general pattern to describe how to read a number. So like, this number there's nothing to it. It's a base 10 number. But this is also how you interpret a number in any base. Depending on the base, what are you changing? All you're changing is the base of the exponent. If you're dealing with a base 7 number, you're changing the tens to sevens, but you're still extracting the digits out of the number corresponding to the power of that position. Is that okay? All right. So now this is what I usually do is I do abstraction. Can someone tell me what does that mean? What does abstraction mean? Okay. I'm not a language expert, so I'm going to defer to Google. Define abstraction. All right, so abstraction is the quality of dealing with ideas rather than events. I would say the quality of dealing with patterns instead of specific examples. That is abstraction. The next one is freedom from representational qualities of in art. No, this is not an art class, so forget about that. Okay, so we are looking at patterns, and that is computer science. That's coding. Coding is an exercise of abstraction. And you have been doing it for at least 3 semesters or 2 semesters for most of you. Because you have to get through what? CISP 300, 1 semester, CISP 360, another semester. So you have been dealing with abstraction for at least 2 semesters. Because a program, okay, any kind of program, including all the homework assignments in CISP 360, is an abstraction of how to do something. Do you know how to find a number in an array by hand? Yes. I give you a very specific array. I give you a very specific value. Can you follow? Can you tell me how you find that value or whether that value is in the array or not? Yeah, I can do that. Now, can you make the computer do the same thing? That is an abstraction because now you're turning what you do by hand as a process into a description of the process. It's a generalization, it's an abstraction, so that the computer can now understand, oh, so the approach, the general approach, the template of doing this is, oh, we have a loop here, there's a conditional statement in the loop, blah, 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 blah. Okay? So you have been doing abstraction already. And in computer science, in math, abstraction is really important because that is basically how people do things. So if I want V to represent what value is being represented, and I use the D subscript to designate individual digits of a number, I can now come up with this general form to say, oh, so the value represented by a number where D subscript something represent individual digits is the summation of blah, okay, which is the product of a specific digit and the power of the base corresponding to the position of the digit. You go like, so what is D of I? I mean, I don't know what is D of I. Well, reading the module ahead of time will definitely help in this case because it is explained in the previous paragraph. So I'm just gonna skip to the part where it is actually important. We use the notation. Oh, okay, that's a typo. Negation. What is a negation? It's a notation. Okay, so we use the notation di to represent the digit that indicates the quantity of, in this case, it's base 10, 10 raised to the power of I. So let's focus on just that sentence and see if we have any questions about that specific sentence. So let me move here. We use the notation, negation. Okay, there we go. Do we have any questions about this sentence? So this is where, rad can come in handy because this is a simple sentence. Rather, it's not complicated. Most people would say, I know every single word except for negation because it's a typo. Okay, but what does it mean? Okay, are there any questions about this particular statement? We are all good. Okay, I'm not seeing anyone having giving me an indication that we might want to slow down here. Okay, so I'm not seeing the indication. So with this notation, then when we refer back to this number, d of 1 is referring to this one. This is d of 0 because the 6 is telling me the quantity of 10 to the power of 0. Okay, and then we have, likewise, we have this is d subscript negative 1, d subscript negative 2, and then d subscript negative 3. Okay, so once we have this notation of being able to refer to individual digits in numbers, then the value represented by a number is going to be represented in a sigma or summation form. Okay, so this is another point where I need to pause to make sure everybody is familiar with the sigma notation, which may or may not be the case, right? So you have to let me know if you're going like, okay, I'm not really sure what the sigma notation is. I can illustrate it. I can explain that. So are there any questions about the sigma notation? Nope. Okay. All right. So don't be shy, okay? Because I am not a mind reader. I cannot tell. I can tell from facial expression, but sometimes that may not be expressed. So if you want me to kind of go over this, we can definitely do that. Okay, I don't see any questions. Okay, so there's another thing that is kind of awkward here. It's like, why would we go from negative infinity to positive infinity when the number clearly only has 5 digits? maybe we should change this to from -3 to +1, and we're good. Why go from negative infinity to positive infinity? Well, the reason is the number inherently has an infinite number of digits and an infinite number of digits extending to the left hand side, extending to the right hand side as well. It's just that what do you think would those digits all be in this case? They're all going to be zeros, okay? And then you end up with 0 times 10 to the power of something. It does not contribute anything to the sum. So why do I want to waste my time to write an infinite number of zeros on this side and an infinite number of zeros on the other side when they don't matter? And that's why they're not written. But just because they were not written does not mean the number cannot have those additional zeros. So that's why I go from here to here, because theoretically speaking, a number can have an infinite number of digits. Go like, I don't think so, Tack. Every number has a finite number of digits. Give me an example where a number has an infinite number of digits. Easy. Pi. It's easy as pie, as they say. Why do you think I say that? You go like, pi, it's easy. It's 3.14. So what's so special about 3.14? 3 digits, we're done. No. I see some people turning their head, and some people go like, I'm not sure what you mean by that. What is pi? The number. Not the kind of pastry you can buy from Costco. So now I want to go to Costco. So what is pi? Okay, so we have 1, 2, 3, 4. Those are counting numbers. We have 0, 1, 2, 3, 4. Those are the natural numbers. We have -1, 0, 1, 2, 3, 4. Those are the integers, right? So, and then we have real numbers like 1.6 and so on. Those are all in the set of real numbers. But the set of real numbers include rational numbers, and what? Exactly. So there are rational numbers and there are irrational numbers. So what are irrational numbers? Okay, I should say the opposite way. What is a rational number? What is the characteristic of a rational number? It is rational, obviously. Now it can be expressed as a fraction where the numerator and the denominator are both integers. That's one way to look at what a rational number is. So what we are really saying is pi cannot be expressed as a integer divided by another integer. So if you want to know the exact value, if you want to express the exact value of pi, it goes on forever on the right hand side after the decimal point. Okay? You go like, okay, pi is something that mathematicians worry about. Give me another example of a irrational number, something that will take an infinite number of digits to express. Easy. The number of days in a year is 365. No, it's not 365 because if it was that, we wouldn't have leap years. You go like, okay, fine, every 4 years is a leap year, so it's 365.25. No, because if it were that, we wouldn't make a special occasion of every 100 year is not a leap year. You go like, okay, so we factor that in, so now it's rational again. No, because if it were rational, we would not make another exception to the rule of every 400 years is leap again. So all of those rules are an approximation, okay, to get to the actual value of how many days there are in a year. Because why do you think nature would use a specific rational number, of how much time it takes for the self rotation of the Earth versus the time of the Earth going around the sun? It makes no sense whatsoever that that would be a rational number. If that was a rational number, then I would say, I think we're living in a simulation. Because it really has no sense why it would work out that way. Of all the values that we can choose from the real numbers, it is a rational number. Unlikely, extremely unlikely. Okay, so yes, I digressed. But you might find some of these digressions to be useful later on. All right, so we make another generalization. It's like, okay, Jack, this is only dealing with base 10. Can you show me something that will work with any base? Okay, we represent the base as a variable b. Can we make this more general so that we can deal with any base? Oh, that's an easy one. Just change the 10 to a b. So the b is now the variable representing the base that you are dealing with. Are we okay so far with all of the abstraction? Because this is the most important equation because it relates the value being represented by a number using the digits, the base, to come up with the calculation. Now, it's really simple as a sum of products between the digit and a power of whatever the base is, but this is what we have been using all along. Okay, when do you start to know how to read multi-digit numbers? Like 20, 25. Oh, I have 35 classmates in my class. Okay, the 3, 5 in that particular order. When did you start to learn the multi-digit numbers? I know it is elementary school for sure, right? So we have been using this equation basically all our lives. It's just that no one might have presented it in this way prior to this class. All right. So the next question is, okay, some of you may have this question. It's like, okay, so we have talked about base 10. We have talked about base 2. Base 10 is easy because we've got 10 fingers and it's just a tradition that is really hard to stop. And then base 2, we kind of understand it too because the logic gates can deal with high voltage versus low voltage or the presence of a voltage, and we translate that into 0 and 1, and then true and false. So binary kind of makes sense. Okay, we can only see whether something is on or off. Okay, cool. Are there any other bases? There Can we have any other basis? I'll change the question like that. So yes, we can. Okay, indeed, in computer science alone, we have these other bases. So this is C notation. So I'm just using C notation here. So we'll say 45. This is in base 10. If you want to express a base 10 number in C and C++, you don't need anything special. Okay, the compiler automatically make the assumption that okay, we're specifying numbers in base 10. But if you want to turn this into an octal number, which is base 8, you can do so in C and C++ as well. A prefix of 0 tells the compiler that what follows is a base 8 number. So as a base 8 number, I'm going to go through the math here. 45, how many 8s do we have in 45? We have 4 8s, okay? And then after we take care of the 4 8s, which is 32, what is the remaining portion? We have
You have
1 8 and 1 4.
you have 40.
Huh?
Eight, you have 5 8, so you have 40.
5
8
times
times 5 is 40.
8 times 5 is
Oh,
40.
right. So there are 5 8s. Okay, thank you. You can see how my arithmetic sometimes can be wrong. So we have 5 8s, and then after we take off the 8s, we are down to 1s. So how many 1s are left after the 5 8s? We also have 5 1s. So 055, okay, if you type that in C++, it is giving you exactly the same value as 45 in decimal. But then we can also change this to hexadecimal. So hexadecimal has a prefix of 0x, lowercase or uppercase. So hexadecimal means, hexa means what? 6, and then deci is decimal 10, right? So deci is 10, hexa is 6. So hexadecimal is 16. So base 16. Wow. We don't even have enough digits for base 16, right? Well, we borrow things from the alphabet, okay? So after we go from 0 to 9, then we go to A, B, C, D, E, F, okay? So in base 16, what is 45? How many 16s do we have in 45? 2, okay? So after we take off the 2 16ths, which makes up the 32, we have 13 left, right? Okay, great. 13 is less than the base, so we just need a digit to represent it. But what digit are we going to use? Let's see. 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have just exhausted all the digits, right? Then you go like A, and then B, C, D. So the letter D in hexadecimal represents what we know as 13. So in this case, 0x2d in C++ is also going to give you exactly the same thing as 45. In other words, we do make use of different bases, okay, in programming. This is not just a theoretical topic that Tech likes to talk about because it's in the syllabus or in the curriculum. This is actually useful, okay? So why do you want to use base 16 of all bases when you are writing your programs? Why do you think that is the case? Well, there's one more thing first. We'll also look at this as a base 2 number. Now, in C and C++, there is no intrinsic way to represent a number in base 2, but GDB does. Okay, it's a debugger, that most people use to debug their program, but GDB does understand base 2 number with a 0b prefix. So, what do you think 45 is as a base 2 number? So we start with 32, okay? So we have 132, moving down to 16. So once we take off the 32, we do not have a 16 because we only have, what, 13 left, okay? So we have, oh, wait. So we have a 16, we have a 32, no 16, 1, 8, 1, 4, and 1, 1. Okay, let me double check. So we got 1 plus 2 plus 4, which is a 7. 7 plus 32 is not what we want. Okay, so I messed up somewhere. Okay, so let's do this one more time. Okay, so 45 has 132, 0 of the 16s, and then we have 1 of the 8, and then we have 5 left. So we have 1 of the 4, we have 0 of the 2, and then we have 1 of the 1. So let me just kind of give you the dotted line here so we can clearly see which digit is corresponding to which power of 2. All right, so let's double check again. 1, 4 is 5, 5 plus 8 is 13, 13 plus 32 is 45, so that is correct. What about base 7? Okay, we only got about 2 minutes left before the end of the lecture. So no one's saying it's going to use base 7, but just because it is insane does not mean it does not exist. So we're going to use an example using base 7, okay? But it's not practical. It is not practical. It's really strange, it's really odd, but knowing how to do this conversion really helps to prove that you already know what is base conversion. So I'm just going to pull a number out of my head, 123 in base 10, okay? And this time we are dealing with base 7. So just like I make a table like this for base 2, I'm going to make a table for base 7. So 1 is 7 to the power of 0, and then 7 is 7 to the power of 1, 49 is 7 to the power of 2. I believe that is sufficient already, okay? So now we look at 123 and ask, how many 49s can I fit in 123? What do you think? Can you do your mental math with division and all that stuff? You don't need to do it really fast. There are 2, right? 2 of 49s, okay? So it has 2 times 49. And once we take care of the 2 times 49, which is what, 98, how much do we have? So 98, so 123 minus 98 is 25, okay? So then you ask, how many 7s do we have in 25? 3 of those. So once we take care of the 3 times 7, which is 21 in 25, we have 4 left. So we have 4 times 1. So now we have 2 times 7 to the power of 2, 3 times 7 to the power of 1, 4 times 7 to the power of 0. Oh, okay. So now we actually have the D0, D1, and then the D2 when B is 7. The base is 7. So that means, okay. So now we can rewrite this entire thing and say it is 2, 3, 4 as a base 7 number. So like that. Oh, okay. It is time, but it is good to kind of let you guys know in a practical situation who is going to use base 7. The answer are drunk octopus or octopi, because drunk octopi needs one tentacle to hold on to the bottle, and then only with 7 left to do the counting. And hence, even though it has 8 to begin with, it would use base 7. So that means our ancestors were not drunk most of the time, because otherwise we would have base 9, because you got to have that hand holding onto the beer. Oh wait, one hand is 5 fingers already, so we would end up with base 5. All right, so now we're going to move on to the lab for today. And all right, so the lab for today is a little bit okay, reset student, leave student view. There we go. So the lab for today is based on the lab on Tuesday. So that means if you did not finish the lab on Tuesday, it would be really hard to get on the lab for today. So I'm going to give you the solution to the lab on Tuesday using the announcement. But before I do that, I will unlock. Oh, this is the wrong class, isn't it? Yep, that's the wrong class. Let me go back to the right class. There we go. Oh, you cannot see it because I was on the wrong screen to begin with. Okay, leave student view. Go back to the class. Network error. Great. And then we get on to nand2 and also the file submission corresponding to that one. And I can show you what access code you need in this case is nandroid. So it's just like Android, except with an N in front of it. You can think of it as not Android, right? Because the N stands for negation. So we have nandroid as the access code of today's lab. I will take off this. I will remove the screen in just a moment. So you should have access to this one already. And then I will send the entire class the solution of the lab on Tuesday. So let me make an announcement. And we'll name this solution of the NAND lab. Okay. See attached. All right, so where did I put that? All right. I think that's it. There we go. There we go. Okay. So if you, for whatever reason, do not want to use your solution on Tuesday to start with the the lab for today, go ahead and use my solution. That's okay. And that's it. And I'm gonna stop the recorder unless somebody has a question that I should also record into the recording. Any questions that you want me to be on the record? Nope. Okay, so we're good. All right, so let me turn off the recorder and then upload the video. Does everybody know how to get to the recording of the lectures? Okay, all right, excellent. So let me